Hey guys, welcome to Digital Srini channel on YouTube, and as usual I request you to go ahead and subscribe to this channel because I know you're going to enjoy the content, or you're going to find the content on this channel to be very educational. Now in the last video we talked about pre-training unit using autoencoders. In fact, we talked about concept at a high level. We looked at what autoencoders are and how to plot feature maps to get a good idea of how features look like at various depths. And hopefully we started to realize that the features are rich enough, on pre-trained models compared to random weights. This is exactly the benefit of transfer learning, right? I mean, you transfer the learning from one model to the other. So we trained a autoencoder in the last video and got a good feeling for how the features look like between random weights and trained model. In this tutorial, in this video, let's go ahead and train an autoencoder, get the weights from the encoder part, and transfer those or use those towards training a unit and see if that really helps. Okay, it may not help you in improving the overall quality of the results. Maybe it does a little bit, but it definitely speeds up your training process, especially if you put in a lot of effort in training your autoencoder at the beginning. If you have a million images of satellite images or electron microscope images, or whatever the type of images that you're trying to segment using UNet. By the way, I keep saying UNet, but you can use exactly the same philosophy for classification. If you have a whole bunch of images, but they're not labeled, yeah, if you find a data set of 10,000 images that you relate to, hey, these are all like cancer cells, right? Go ahead and train an autoencoder, because for autoencoder, you don't need labels. This is why training this would be pretty amazing, because then the encoder learns how the features would look like, and then your subsequent training on whatever application would be that much faster. Okay, it's all about speed. If you're doing this on a one-off thing, it doesn't make any sense, right? But then the idea here is you're going to work on that type of data set over and over in future. So you want to train, save time ahead of time by training on autoencoder. Okay, enough about that. We'll get to coding in a second, but I want to show you the results. For those of you who are in a hurry, if you want to be convinced that, hey, this is still something you want to give a thought, let me quickly show you a couple of results. So here you see the orange line is for validation intersection over union for the pre-trained network, okay, where we are using the weights from autoencoder. And the blue is for the random weights. So blue is what we would normally do. And the orange is what I am proposing that you should do. Why? Because if you are looking at getting 82% intersection over union in this case, and by the way, if I leave this another 25 epochs, this may actually go up a bit, but let's just focus on what we have here. 82% intersection over union. Our pre-trained network got to 82% in 7 epochs for my data set. I'm not saying you would get your results in 7 epochs. The data set I'm working on, I got 82% IOU in 7 epochs. And also this curve is a bit more smooth compared to the other one down here. Now, if I'm starting with random weights, it took about 23 epochs to get to a similar intersection over union value or a similar metric. The point I'm trying to make is it's faster, but not necessarily higher quality results if you are using pre-trained network. You may accidentally end up there, but that's not the intention of using pre-trained weights. Okay, so that is the lesson here, and let's jump into the code and see how we can put this thing together. And I am showing you the screen from my last video, where we left off by printing out or showing or displaying some of the features on the 32nd layer, right? The depth of 32, which is the last layer in the encoder. And you can clearly see these weights are the pre-trained and these are just random. So no feature information here, but when you have pre-trained weights, you already start with some feature information. Okay, so enough convincing you that this is something that you should be considering. Now let's clear everything and start from scratch. Okay, so now we have nothing. All we have is a whole bunch of data, like a folder full of data. let me go ahead and show you what I have. 256, which ones are we working with? 256 patches. I have no masks. All I have is images. That's it, right? Just images. A whole bunch of images. I dumped all my 4,000 images into this folder, and it doesn't know anything about any of these gray levels. Remember, for semantic segmentation, we need to label all of these. So far, I just have nothing. This is it. Okay, now what? Okay, now let's go ahead and import the right libraries right there. Let's get started. This is again nothing tricky, pretty much the standard libraries that we would use if you want to put together a deep learning model. Okay, at this point I'm going through data mito/images data. In fact, I showed you the wrong folders, sorry about that. I'm using data mito/images, these ones, okay, because I have labels for this one, so we can test out the unit later on. So these are the images I'm actually dumping, not dumping, I mean I'm going to use right here to train a autoencoder. Previous example, single image. Here I'm just training on a whole bunch of images. That's all I'm trying to do. First of all, we need to capture them as a NumPy array. So let's go ahead and load them. There you go. I have all my 1600 images right here. Yeah, I have 1600 images, all of those in a NumPy array, and I already divided them by 255, so they're kind of scaled to 0 to 1. Why am I taking a subset of this? Because I just want this training to be a bit faster. Of course, you want to train on the entire data set. Even consider using loading from the, using data augmentation, in Keras to load images in batches and all that. Do the normal good practices. But here I'm just dividing, I'm just extracting 500 images, so the training is faster. That's all. Now, we need to build our autoencoder. So far, we just have image array. Now let's build an autoencoder and train the autoencoder. So here it is. So I already talked about this in the previous tutorials. Let me go back and quickly explain that. So all I have here is a few functions to build a model. The first one is convolutional block, where I have two convolutional layers defined with batch normalization and activation. That's it. So this function returns the output of two convolutional operations. And then I define something called encoder block. Encoder block is nothing but whatever I just showed you here, plus max pooling, okay? Plus max pooling, right? This is how you build your network. And the decoder block is exactly opposite path, right? You can either use upsampling or conv2d transpose. In this example, I'm using conv2d transpose, and then the convolutional block that I showed you up here. That's it. That's my decoder block. When I put encoder and decoder together, this is my autoencoder. And that's exactly what I'm doing here. So what do I want to do? 1, 2, 3, 4, 5 encoder blocks as part of my encoder. So I'm putting 5 of these together, and as part of decoder, exactly the same, but symmetrically opposite. 1, 2, 3, 4, and the fifth one is the output layer. Okay, so there you go. And this builds the autoencoder down here, where I say my input is the input image, and this is my output. Obviously, the output is nothing but my whatever comes out of the decoder, right? So that's what we are trying to do, build a decoder and provide the output from encoder as the input. Okay, everything here, I talked about it in the last video. So we are going to import, build autoencoder, build only the encoder, right? This is important. I'm importing this, where it gives me the entire autoencoder. I'm only importing the encoder because we'll extract the weights later on. And I'm also importing unit. Well, let's go ahead and talk about unit. You see, this is my unit I'm building. So the encoder part is exactly the same. This encoder part is exactly same as this. If you see, if you look, as this one, S1, P1 to encoded P4, 1024, P4, 1024. Except my decoder is different in this case. Why? Because in unit, in addition to decoder, you have a skip connection part. That's the second input that we need to give right here, skip features part. What does skip features mean? It's nothing but convolutional outputs that you're getting from the encoder. That's exactly why my encoder up here, if I can find it, yeah, my encoder up here is giving me two outputs. One, the output of convolution block, and 2, the output of max pooling part. The output of max pooling directly goes to the next layer. The output of convolution block goes to the next decoder that it needs to connect to. Okay, this is only for UNet. For regular autoencoder, you don't care about that. You only care about this part. I know I confused you. So go back, watch this a few times, learn about UNet, learn about autoencoder. But that's exactly what we are doing here. Okay, so the decoder is very similar to autoencoder decoder part, except it has skip connection at this. That's it. Okay, so now you know what's inside my models.py. I'll just share that with you anyway. So let's jump back into our main part of the code. Okay, so so far we just loaded our image array, which has 500 images ready to be trained on. What are we training it on? First, we are down here. We imported the autoencoder, encoder, and build unit. Now let's start to building these. So let's build autoencoder, define an autoencoder model. How do you do that? Well, just build that onto my image shape. Let's go ahead and do that. And then compile the autoencoder. We did this in the last video, exactly the same, nothing different except for the dataset part. Instead of single image, multi-image. So we're going to use mean squared error loss because that's what we are trying to look at, right? My final image, original image, they need to be the same. So look at the mean squared error, and metrics would be accuracy that we are tracking. So let's go ahead and compile our model and print the autoencoder summary. Again, I just want to make sure you understand that we're going from 256, 256, 3 to 64 filters, right? That's what we defined. And then 128 filters, 256, 512, 1024, and then back down all the way until we get our original image back. This is autoencoder. Okay, so now let's go ahead and fit the autoencoder. Don't worry, this will take some time. So I have already done that. So we'll just load the model in a second, but this should go pretty straightforward. Okay, and then I saved it so I can load it right now, which is down here. So let's go ahead and load the model, and I put compile equals to false. So we're not training it, we're just using it to predict. So let's go ahead and load this model. So this is the entire autoencoder model. We have 63 layers in autoencoder. 32 belong to encoder, and the remaining 31 belong to the decoder part. Okay, so we have 63 of those. So I loaded this, and now out of curiosity, let's go ahead and load some random images and reconstruct them using our autoencoder and see if it's doing a decent job. Okay, we are still talking about autoencoder. Oh, that's not bad. This is the original image. That's the reconstructed image after training, only with 500 images and not that long. 100 epochs went pretty fast actually. Oh, that is very good. I'm impressed with how good of a job autoencoders actually do. That's why you can use these for anomaly detection, for example, because you look at the reconstruction error and where is that reconstruction error happening. So that gives you anomaly, and this can be used for denoising and other applications, but there are better approaches for denoising. So let's not deviate our topic here. So I hope you're happy even with this result. I'm not looking for exact same image here. It would be nice if it is, but this is great. It's enough for us to be confident that the model has been trained to some extent, so the features that we can expect can be easily used for UNet. Okay, now that we have a trained autoencoder, how do we take the encoder part, the weights for the encoder part, and transfer them to the unit, the encoder part of the unit. Okay, so let's do this in a stepwise way. First, let's from models import build autoencoder. We already did that, right? Build autoencoder. So this is basically a redundant line. So let me comment that out. And load model. I don't know. I keep doing this. I keep importing things. Okay, so let's go ahead and load the model. We saved it up there and we loaded it here once to check it, but let's go ahead and load it. Okay, and the next thing we are going to do is we are going to build an encoder only. So here, please stay with me here. My input shape for these images is 256 by 256 by 3. Yeah, and then my input image is input shape equals to input shape. Yeah, this input is models dot. Where is my input? This is important so you don't confuse this. Yeah, that input. Yeah, this is from my keras.layers Okay, and then the model is keras.model. So I'm going to import this. Again, you may think this is basic, but again, some of you may benefit from this. Okay, so I defined my input that goes into my encoder. So what is my encoder? Let's go to models. And if you look at build encoder only, right? So we are just trying to build encoder right now. It needs input image, which is exactly what we just defined. So let's go ahead and build encoder. Now let's define our encoder model. It just built the encoder. Let's define the encoder model as input image, and output is whatever the output that comes out of this encoder. This is the model that I'm defining. And let's go ahead and print the summary of this model. Yeah, so there you go. This should be exactly half of autoencoder. Yeah, so there, so 256, 256, 3, and when you go down, it should just stop at 16, 16, 10, 24. That's it. And if I scroll up here, the previous model, this is where we are chopping it off. Okay, the top part. Okay, so why did I build encoder only? When you do that, when you build something, that comes with random weights. I haven't defined any weights yet, so as you probably know where I'm going now. Now I want to take those weights and transfer them here. How do you do that? First of all, let's look at number of encoder layers. Number of encoder layers, 35 right there. Okay, so number of encoder layers are 35, which means in my autoencoder, from my autoencoder, I need to take the weights from the first 35 layers and bring it to this model. That's the reason I'm finding that out there. And here is the line, a couple of lines, or single line, or two lines right there, that helps us transfer the weights from the autoencoder model for the first 35 layers to the first 35 layers in the encoder model that we just defined up here. Okay, so these are the lines. So basically, in zip these two, L1 and L2, that means L1 corresponds to my encoder, L2 corresponds to autoencoder. So L2.getWeights, get the weights from autoencoder, and then set them as the weights for my L1, which is my encoder model. So when I do that, now it replaced my default weights or random weights with these new ones. How do we know that? Let's verify it now. Let's go ahead and verify it. My autoencoder weights, again, autoencoder is the one we trained. Encoder is the one that we just created. I know the same names can be confusing. Okay, so from autoencoder, let's get weights from the first layers right there. And let's do exactly the same for our encoder weights. Okay, so if I go to autoencoder weights up here, let's see if we can open this, and then encoder weights, they're identical, as you can see. I mean, they should be. That's exactly what we did up here. This is how you take the weights and then assign to a different model. And now I can go ahead and save this, which we'll do in a second. So we did that, and now let's go ahead and save these weights. And this way, I'm saving the weights for my encoder as in this example, I'm saving them as a NumPy array. Okay, so this is how you can save the weights and check the output of encoder. Again, this is, if you want, you can check the output. I mean, I'm reading an image, a test image, and then all I'm trying to do is apply my encoder model onto this test image, and then you can plot it out and then see. This is just, again, one of those sanity checks that you can do. But we are not done yet. I mean, we want to actually transfer the weights to unit. In fact, you could completely ignore this encoder step, and you could have directly went from autoencoder, take the first 35 layers, come down to unit, take the first 35 layers, just transfer the weights, go ahead and do that. I want to make this a bit of an educational video, so I'm going through this in a few steps to make sure that there are no gaps in the knowledge here. That's all. That's it. Okay. Now, let's define a unit with the same encoder as autoencoder. Again, the idea here is we are going to define the unit with random weights and replace the first 35 layer weights with the encoder weights that we have. Pretty straightforward. So that's what we are trying to do. Go ahead and define my input shape, build unit. How are we building the unit? We already discussed that. We are building a unit this way with the same encoder, so I can transfer the weights. That's the point here. So build my unit. There you go, it's building. And just to show you, up to this point, 16, 16, 10, 24, it should be exactly same as our previous encoder. After that, you get some other layers. We'll see that in a second. So to verify that the layers are the same between the unit and autoencoder, let's go ahead and print the layers. How do you print the layer names? It's just basically, where is it? Unit model. There you go, layer.name. Layer.name will give you the layer names. And I put this in a for layer, so it goes through each layer, and we capture that as part of a list. And I'm doing that for autoencoder and unit. Okay, so let's go ahead, run this. And now let's open autoencoder layer names and unit. I can see some of you thinking, oh my God, this guy is covering a lot of basics, not a video for me. That's fine. I watch videos where I think I know something about it, but then when I watch it, I'm like, that's what, every video has a gold nugget. Oh, that's my life philosophy. Okay, so 0 to 14, the layers are exactly, the names are different. I mean, this one says input 11, this one says input 5, because it assigns these names, the numbers. But then look at the layers here, all the way up to 35, right? All the way up to 35, 34, 35, con 2D transpose, con 2D transpose. And then comes con 2D something, 36th layer in my autoencoder. In my unit, the next layer is concatenate. But up to that point, it's exactly the same. It's exactly the same. So far, so good. Again, this is all sanity check. Okay, now we are going to do exactly the same as what we have done up here, which is for unit from the autoencoder model, transfer those to my unit model. Yeah. Again, you can completely skip this part if you want. This part is, I just wanted to show you how encoder and relates to autoencoder. But here we are directly jumping from taking our autoencoder model, assigning the weights to unit. So you can just do this step. Okay, so this is what we are trying to do, and let's assign the weights to the encoder part of the unit. And now you can go ahead and compile your unit model and save the weights. Okay, so let's do that. So let's import the atom right there that we are going to use as optimizer. And for losses, when it comes to unit, I love this library called segmentation models. And from here, I'm going to use categorical focal Jacquard loss. So focal Jacquard loss is basically, maybe I should have imported binary focal Jacquard loss, because my unit training right now is going to be on binary Jacquard loss. But anyway, be careful about these. But I'm going to use categorical focal Jacquard loss. This works great for multi-class classification. Mine is binary, so I'll have to change this to binary. The metrics I'm tracking is IOU score, and both of those are available as part of the segmentation models library. So go ahead and use that, or you can use whatever compile that you would like. I mean, whatever loss functions that you think are appropriate for your problem. Okay, so let's go ahead and run that line. We haven't done that, and let's print the model summary. So you can see that the model is pretty much, again, we have seen this many times. So let's save this model. So far, what have we done? We trained an autoencoder on 500 images, and we saved the autoencoder, the encoder part of the weights into our unit model that we just defined. So here we defined a blank unit model with random weights, and we populated the encoder part with the weights that we trained on autoencoder. And now we are compiled the model using the losses and everything, and we are going to save the weights. So when you do that, the encoder part of the weights will be the ones that came from here, and the decoder part of the weights would have been random. Some people make the encoder to be non-trainable during unit and only train the decoder. So that's one way of making it faster. If you're confident enough that your images look very similar to the images that you have trained on autoencoder, you can do that. Okay, you can set your encoder. I think there are also tricks that you can say, okay, for the first 50 epochs, don't train the encoder, only train the decoder, and then train both together. It's up to you how you want to do that. But let's save the weights right here, which I have already done. Now let's train a unit. Okay, again, I promise this video won't be any much, maybe 5-10 more minutes because we have done bulk of the learning already, and this is something that we have done many times. Okay, so let us start from scratch, because what is the assumption? We have already done that. At this point, I have already done my weights and everything, it's there. So all I need to do is load my unit with partially pre-trained or pre-primed weights and then continue. So from now on, this part should be very straightforward. What I'm doing here is now I'm going through these folders, images and masks. This is my unit, and I'm capturing them as NumPy arrays, dividing them by 255, which I should do in a minute, and getting my data set ready for unit. Okay, so this part you're familiar with, and then I'll divide my data into X-train, X-test, Y-train, Y-test, so I can train this on, train my model. So let's go ahead and get our data set ready. I don't even know why am I doing this, because I already trained the model, so no point, but it's important for you guys to see the process. The more you see this, the more it becomes a habit, and habit is a thing that you cannot change easily, and good habits, that's why, are very good. Okay, enough life lessons. Let's move on. So at this point, what I'm trying to do here is define two models. One is the one that starts with random weights, meaning I'm just building a unit, and the one that we use with pre-trained weights. What am I doing here? Define a model with random weights. Let's go ahead and do that. Define a model with random weights, which is basically build my unit. Yeah, that's the random weights. Oh, build unit. Let's run these lines. Okay, so at this point I have a unit model called random weight unit model, and then I have random weight printing out the weights right there. Unit model weights, or saving that, and then I'm defining a unit model with pre-trained weights. Okay, so here is something with pre-trained weights. Again, up to this point it doesn't have pre-trained weights, right now it's only a model. Now I need to load the weights. So when I load these weights, the first 35 layers is populated with the new weights. So let's go ahead and do that, and then let's assign the weights of the first two layers, like this and this. Why am I doing this? So I can compare these two and say, hey, see, the weights are different. Okay, and let's also load the encoder weights, right? Remember we saved our encoder weights as a NumPy array. You can also open that and compare those. So that's exactly what I'm doing here. Hey, if my pre-trained unit model weights, which is this one that we just defined, is equal to pre-trained encoder weights, just say both weights are identical. If not, just say something is wrong. Again, sanity check right there. So it's doing, and both weights are identical. So we know that, hey, we did successfully transfer the weights to unit. And then let's compile both models. The one with random weights, the other one with pre-trained weights. Here I changed it to binary. So there you go. Once you compile these, go ahead and train them. Train two different models and save it. This is exactly what I have done to show you the results earlier. And once you pre-train those, go ahead and plot. Let's do this. I'm going to load both models right here, and then let's see how the results look like on both, using both of these. So let us first start with the random weight model right there, and just plot. And in fact, the random weight doesn't do a bad job. You see, this is the label, and that's the prediction. The random weight doesn't do a bad job. Let's go ahead and print one more and then see how this is doing. So starting with random weights is not bad. Let me go back to the presentation. Starting with random weights, like I just said, is not bad, because eventually you'll probably get the same type of accuracy. It's just that it takes a little longer for the random weights to get there compared to the pre-trained weights. So this is for these images. If you have thousands and millions of images, maybe this separation is not just like 7 to 23 epochs, but maybe 1000 to 5000 epochs. But I just want to make sure you understand this process. And sometimes you'll see the results change in the quality. Changing the quality of results. So here is random weights initialized. You see they both look very similar. This is not bad, but if you look at how the results would look like using pre-trained initial weights, this is much better in the same amount of time, right? So let's get back to the code and then load a few images to see any of these differences. And then there you go. That would be the end of this video. So we are still looking at random weights. So let's see an area where it's not. Okay, so this is an area where it's not doing that great, but I don't know, do we do much better with a pre-trained? Because down here, you see how it's showing a whole bunch of stuff, but there is no mitochondria there, but it can be tricky. And down here and up here. So let's change the model to pre-trained right there and work on the same image. Yeah, there you go. So here, this is random weights. This is pre-trained. Random, pre-trained. You can see how much better the pre-trained weights model is in 25 epochs. Maybe if I go to 50 epochs or 100 epochs, there isn't much of a difference between these two. But you can clearly see the quality is also much better in this example between these two. Yeah. And especially if you take this and you keep segmenting each tile and put all the tiles together, that's going to look horrible on this if you do that with this image compared to what you do with this image. Okay, this I didn't expect this to be a half an hour long video, but I thank you guys for sticking around, and I hope you really learned something new. And I really think that this is a great way of leveraging unlabeled dataset. If you have unlabeled dataset, this is a great way of leveraging. If you have labeled dataset, go ahead and train it on a UNet, because when you're training an autoencoder, you are spending time. Yeah, but if you have unlabeled, the best way is to train an autoencoder, get all the features, and then label only like, I don't know, 50 images and see how good you're actually going to get, when it comes to semantic segmentation. Do not forget that pre-trained encoder can be used for classification. All you need to do is add a couple of layers for prediction and convert that into a classification problem. Okay, so pre-training this can, again, this is the core of transfer learning. This is the essence of transfer learning. So thank you guys, and I hope you again learned something useful. Subscribe and like this video. Thank you.